Okay, so we are back for the last part of the Rust lecture on GPU, and then we'll move on to Julia. So last chance for you to understand all of this black wizardry.
I stared at the abyss, and the abyss stared back. That's the spirit of GPU programming.
So Hadrien, it's yours.
Thank you for the introduction. So, you may not know, but actually in the teacher team, who also calls itself the Muppet Show, we have a saying that everyone has a very bad faith. And one of the essence of bad faith in programming is when you say, okay, my technology may look horrible, but you see when I put it on a more complicated problem, it scales better than the other one. This is exactly what I'm going to do here by showing you how Vulkan, which we have seen on a simple number squaring example, would scale to a more complex example, the Gray-Scott reaction simulation. Let me mute this for now, because it's always going to be annoying. So, earlier, I mentioned that when we say that Vulkan or OpenCL or whatever is verbose, it's also a bit of bad faith, right? We should differentiate two different things in those APIs. The setup that you can easily share between multiple applications versus the setup that you need to do for any new computation. And I claimed at the time that the instance and the context part of my Vulkan setup is relatively generic and will not need that many changes to handle other computations. This is where I show that this claim has at least some substance by showing that the only thing we need to change to this entire code base to support our fantastic console progress bar, the only thing we need to change in this whole setup is to add the ability to support our textual progress bar. Because you see, we all love nice text user interface. They look beautiful, they make us look smart, but they come at a terrible cost that any programmer who uses them knows, which is that as soon as you start using them, you break the most important functionality of all programming language, which is the ability to emit text on stdout and stdr undisturbed. The indicative developers who handle these nice progress bar for us on the Rust side thought about it, or their users complained about it. I don't know the story. And so they provide a nice utility that we can use, where we take a progress bar, we call the suspend method, we provide a callback, and we say, okay, I want this callback to execute as if there were no progress bar, and then magic happens, and the rendering is interrupted, text goes nicely below the previous progress bar, and then the progress bar resumes, and the rendering is perfect. And what we need here is to integrate that into our Vulkan logging code on any other textual diagnostic we may want to insert in our application, so that whenever we feel like printing something to stdout and stdr, we call this utility. I show how that's done. I have two versions of this exercise, one for Rust beginners, I need to fix this, and one for people with more experience in Rust. The idea is, in one case, I give a pretty strong hint. If you think you know the language already, you may want to try the other version, which has less hints.
You know what you have to do.
And then I move to the first meaty part, which in the interest of time, I will have to cover orally right now as well. And that's how our compute pipeline infrastructure is going to change when we move to the Gray-Scott reaction. Here, we will not attempt to deduplicate code between the number squaring computation and the Gray-Scott reaction computation, because this is the point where we start using the language genericity features too much, and then people who are not familiar with genericity get lost. So instead, we will accept some degree of code duplication in the interest of accessibility. So we create a pipeline module, register it, and we get started again with GLSL, our friend, our only friend. As usual, we need to say which GLSL version we are using. But now our data interface is going to look a little bit different. Because remember, in the Gray-Scott reaction, we now have 2 inputs and 2 outputs. The inputs are the former version of the concentration of the U and V chemical species. And the output is going to be the version of the concentrations after the next simulation step. We can do this in GLSL. Because we have multiple inputs, we should be nice to our compiler. Since it's not a Rust compiler, it expects us to be nice by saying that our inputs and outputs are not going to alias one another, which means that lots of interesting optimizations become possible at the hardware level, at the compiler level as well. And we are also going to use GLSL feature, which should not improve performance for any self-respecting compiler, but which will make our code a little bit easier to maintain. And this feature is read-only and write-only. So in most programming languages, you have a base case, which is for Rust read-only, for most functional programming languages as well. And for most imperative programming languages, it's being readable and writable. And in either case, when you want to go away from the default case, you need to add a keyword. GLSL, at least for buffer inputs, tries to be symmetrical. So if you want to only access data for reading, it's read-only. If you want to only access it for writing, it's write-only. So far, so good. The last thing we are going to need is we are going to need 2 inputs and 2 outputs. And now you may be wondering why I am not able to put 2 different array members inside of my buffer. You know, why I need to have 2 storage blocks, each containing a member called data. And the problem here is that GLSL inherits a limitation from C because, let's be honest, this design is mainly copied over C, which is that in data structure, you are only allowed to have 1 member of variable size, and that member must be the last member. So because of this, unless we are ready to store both the U and V species in the same buffer, which I would not recommend because it makes debugging harder in case you access this buffer out of bounds. It's better to have 2 different buffers, and as we will see, because we have descriptor sets, it will not be expensive anyway. I personally, as I mentioned, don't like to have hard-coded zeros and ones flying around in my code, which is why I will also be defining a pair of constants that let me remind myself that when I'm accessing the first buffer, it's the U concentration, and the second, it's the V concentration. After the memory inputs and outputs, the next thing we want to manage as the CPU-GPU interface are specialization constants. As I mentioned, these can serve 2 different purposes. One, software quality purpose, and one, performance optimization purpose. From a software quality perspective, specialization constants allow us to have less duplicated logic between the CPU and the GPU parts. In particular, we do not need to duplicate our constants because we can just have the constant defined on the CPU side and then set it on the GPU side using the specialization constant mechanism. From an optimization perspective, specialization constants allow you to tell the GPU compiler about information which is only available at the time where the application is started. As we are going to see for Gray-Scott reaction, one example of this is the reaction parameters. We can tell early on, before the GPU code is compiled, by the way, my reaction rate is this and my etc. And then it will be able, the compiler, to optimize our code based on knowledge of certain spatial values. Like, for example, if the time step is 1, as is the case in all of our GLSL implementations, then the compiler will see that we are multiplying by 1 and helpfully remove the multiplication. So here I got a bit wild with specialization constant because they are so great and I put a bunch of them. So as before, we have our workgroup size. This time it's 2-dimensional because our problem is 2-dimensional, and intuitively it makes more sense. If time permits, we'll discuss how this affects performance. It's still configurable from the host side because specialization constants are unfortunately limited to scalars. This means I need to have 2 specialization constants, one for the horizontal dimension, one for the vertical dimension. One thing which the GLSL buffer mechanism does not tell my GPU code is how wide our images are. We know how many elements they contain, but we don't know how these elements are split into rows. So we need to somehow send in those information to the GPU, and specialization constants are another way to do that. We have the reaction parameter. The stencil, so this, since we mostly agree among teachers to use the stencil at last, the same stencil at last, I could have not made this configurable, but it just felt better, to be able to switch between the stencil that is most accurate overall and the one which has the best rotational invariance. I will let my colleague on the back remember the names of each, because I don't. Unfortunately, again, because specialization constants are scalar, it's a bit of a mess. I need to define one specialization constant per element of my stencil. This is fine for interfacing purpose, in the dog sitting in the fire way of this is fine. But for my GLSL code, I don't want to see this. So the first thing I will do is to turn this into a 3x3 matrix, which is much easier to use. And then I have the diffusion rate, which tells you, when you have more spaces of U and V in one place, how quickly does it diffuse in space. And I play the same trick of turning it into a 2-dimensional vector. We have vector types in GLSL. Let's use them. One thing we should decide before writing shader code is what our data layout is going to be. During the CPU course, I mentioned that we have 2 ways to handle stencil computations at the edge of the simulation domain. One way is to adjust the size of our stencil so that, when we reach the edge, we shrink it, and then we don't access out-of-bounds elements. The other way is to add a bunch of zeros around our simulation domain. In the previous course, I show you the first strategy, at least until I introduce the crazy Cindy layout from Pierre. So this time, I'm going to show you the other strategy by adding a bunch of zeros, and this way we can see a bit the trade-offs involved in each case. So to visualize, the idea is that what I want to be able to do is to compute each cell of my concentration table by doing a weighted mean of the neighboring concentration value. And at initialization time, I have set up a bunch of zeros that I will not change anymore. And this allows me to have a regular stencil logic that is the same everywhere. So simpler code, more complicated data. As I mentioned earlier, stencil, pick your poison. When I say simpler code, we do pay something in terms of code simplicity, which is that now anytime we manipulate a 2D position in space, we need to remember to add 1 in the right places. And whenever we manipulate a size, we need to remember to add 2 because we are padding elements on both sides. Because this is a bit annoying, I prepare a bunch of utility, constants, and functions, which will later allow me to have a nicer, higher level logic in my shaders. Such as, for example, the ability to read U and V at a certain position or write U and V to a certain position. And then I move on. There is something new that I did also in this version of the Grayscale computation. If you remember my numbers query program, at the time I said I would like to initialize data from CPU data, because this is the most general way to do things. There are some cases where you will have to do this. This is not one such case. In our Grayscale simulation, the initial data pattern is very simple and is totally within the realms of what a GPU program can easily generate. If we generate it on the GPU, we save ourselves from the trouble of handling the CPU to GPU data transfers and expect overall better performance. Our logic is going to be that we have one GPU work item per cell of the concentration table, including the outer 0 elements. And we are going to spawn work groups that may not evenly divide the size of the image, which means we are going to need to be careful on the edges. Overall, it looks like this. I bring back the saturating sub utility from us because it's cool. And I start, as before, by asking GLSL where I ended up on the simulation domain. So this part is the same as before. I use one GPU work item per output data point. After this, I check if I'm out of bounds, if I'm outside of the target image. If I am, this particular GPU work item will not be doing any work. It will exit early. Then I check if I am on the zeroed edge. And here I use some fancy GLSL Boolean vector logic, which I also did earlier, by the way, which makes this a bit less ugly than it would be in a language that doesn't have vectors at all. But frankly, I still wish we had an inside rectangle function in GLSL. If anyone here is in the Chronos committee, pass the word. Finally, if I am not out of bounds and I am not a 0, then I am a regular data point. And here we find the same logic we had on the CPU side. Couple things worth noting. I cannot share this version directive between multiple GLSL programs. I don't know why, if it's a GLSL bug or a bug in the compiler I use to compile GLSL into SPIR-V. Need to spend a bit more time looking into this. That's not a big deal, though, because the amount of duplicated code remains tiny. I can still share my interface declaration and my constants and so on, and that's the most important part. I would really not want to duplicate this code if I can avoid. Then I write the main simulation task. And here, I want to have you think about something, which is that for simulation, the mapping between GPU work items and data is not as obvious as it was for initialization. I could do this in two different ways. One way is to have one GPU work item per output data points. That's kind of the logic I had in the CPU code. And then for each of these output data points, I will compute the stencil, looking neighboring elements, and so on. The problem with this is that I am going to read the same element multiple times because I'm looking at neighbors. And unless the hardware saves me from myself, this is going to be costly in terms of memory access performance. So I could do it another way, by having one GPU work item per input data points. Now, each GPU work item is in charge of loading the corresponding input. And then these work items need to communicate somehow, the technical term is synchronize, to compute the stencils. Generally speaking, GPUs are better at handling ill-behaved memory accesses than they are at handling lots of synchronization. So my experience as a GPU programmer tells me that most likely the first solution is going to be most performant, especially after I implement an optimization that I have not written in this course yet, unfortunately. But I don't know. So I leave this around as something I would like to get back to later. Assuming I use the strategy of having one work item per output data point, if I use the same schematics as before, it looks like this. So the purple squares represent my GPU work groups. They all have the same size. I need to spawn enough of them to cover all the data points I need to compute. And this will compute a bit too many work items, but yeah, I cannot work around that. I will associate each GPU work item with one data point, one output data point, which means one part of the central region of my data. And this means, I should not start at coordinate 0, 0. I should start at coordinate 1, 1, because that's the first active cell in my table. So I will need some kind of shifting, as I mentioned earlier. And after that, it becomes the same. Each of my GPU work items will be like the red square in this schematic. It will be computing one value at a particular location by loading the input value at the same location and the surrounding value represented by the blue square. Overall, it looks like this. So I start by asking, as usual, GLSL, where am I? GLSL tells me where I am in the grid of work items. That's not quite what I want. I would like to know where I am in my central region, so I add an offset to correct this. Then I check if I am out of bounds with respect to my central data region again. The work items that are indeed out of bounds will need to be discarded. They cannot do any useful work. I load the central value. And then I do a stencil loop where I start from the top left corner, prepare my weights. This will be computed at compile time due to the magic of specialization constants and inlining. And I prepare a place to integrate my Laplacian term. I will also need, for a reason that will later become apparent, to compute the sum of the Laplacian weights. Then I iterate over the 2D stencil. First in vertical coordinate, then in horizontal coordinate, because that's how memory is laid out on GPU. And I read the value at my current position. So starting from the top left corner, I add the offset associated with my 2D loop. I get the corresponding value. From this, I also get the weight that corresponds to my particular stencil location. And I add to my sum of weights the current weight times the value that I'm looking at. So Laplacian as usual. If you remember some previous versions of this computation, you may remember that here I was not just looking at the stencil value. I was looking at the stencil value minus the central value. I don't need to do this. I will end up subtracting my central value over and over again with different weights. It's more effective to just compute the sum of weights and subtract it once. And because floating point is a pain, it's very likely to be more efficient even after compiler optimizations. The rest is quite similar to what you've seen before. I will not comment it further. On the CPU side, I'm going to use Vulkan shaders again. Here I'm using a feature which allows me to load two different shaders with one call to the macro. If I needed to set common parameters, like setting an include path and so on, it would allow me to deduplicate these parameters, periods just for the sake of concision. I did not really need this. As usual, I prefer to have human-readable names for all the magic numbers in my GLSL. It will not prevent them from getting out of sync, but it will make my CPU code much easier to read and adapt later on. And then I can move on with specialization. So remember, before we need to add a command line parameter to set the one-dimensional workgroup size. In VS Code, we are going to need one for the horizontal side, one for the vertical side, because this is a 2D workgroup. I will need to add these options to the main command line option struct of my simulation. And once I have done that, I can set up all my specialization constant. Here, I did it in a way that is less paranoid by the previous one, because the previous one, had like one specialization constant. This one has 17. It would get a bit tedious after a while. Then I will basically copy and paste my setup compute stage function from the last time. It's the same, We need to get an entry point. It's always going to be a single one because we are doing compute pipelines which only have one entry point. And then we need to configure it, and I'm not touching the configuration here because basically it will only benefit Intel GPUs and only if the automatic SIMD width selection logic gets something wrong, which is not that often. There is one thing, however, which I will want to do differently from before, and that's the pipeline layout setup. Earlier, what I did was I said pipeline layout setup is a lot of pain, repeating a lot of stuff that I have already said in my GLSL code. It's good to let Vulkan infer it from my GLSL so that I do not need to repeat the same logic on the CPU side. Here, if I do this carelessly, what this means is that each of my compute pipelines, the one for initialization and the one for simulation, will have a different pipeline layout, which means that I will need to create different versions of my resource descriptor set for each pipeline. That does not sound like something I would like to do, especially on a wider scale with many more GPU compute pipelines. So what I will be trying to do here is to set up a common pipeline layout, which is shared between my two GPU programs. And thankfully, I can do that without giving up on the convenience of Vulkan, because the pipeline descriptor set layout create info, mouthful, that I'm using accepts an array of pipeline stages, not just one. Someone thought about this. That's great. And then, I can check my layout. If it sounds right, single descriptor set, 2 bindings, 1 input binding, just, being paranoid as usual because I don't like the kind of bugs you get when the CPU and GPU code get out of sync. And in the end, I build my pipeline layout and I call it a day. Do we have questions about this? If not, then what I'm going to do is to let you work on this as you see fit for half an hour. As I mentioned, in my opinion, in this sort of course, quality is more important than quantity. If you think you need to spend more time on the previous chapters to understand them better, please do so. It's okay. The material is designed such that you can get back to it later. And you will learn more if you fully understand the previous chapter than if you try to get everything the first time. I see I have no other comments on Discord. So if there are no other questions, I will let you work a bit. All right. So let me maybe cover one more chapter before the coffee break. This way I get a bit more time after the coffee break to get into something I would like to show you a little bit of GPU profiling so that you know what it looks like, because I didn't do it last time. So earlier we saw what it takes to take our Gray-Scott simulation and turn it into a bunch of compute pipelines based on GLSL. But we have the same problem as before. We have a GPU program. We do not yet have data to feed into this GPU program, and that's something we need to fix. Here I'm going to use Vulkan descriptor sets, the way they are meant to be used, which is to say that ideally, whenever I run a GPU program, I would like to only need to bind one descriptor set, and in an ideal world, in a sufficiently complex application, 0 descriptor sets. Here, I cannot easily get to 0 because I have a set of inputs, a set of outputs, and it's changing every iteration of the simulation. I could actually work around this, but at the expense of losing the convenience of the read-only and write-only in GLSL and making all my buffers read-writes. I decided against it because I measured the actual CPU overhead of an implementation, and binding one descriptor set is not going to kill my performance. And if I can have cleaner code, I prefer the cleaner code. Thus, I will have 2 descriptor sets that I will alternate between. One of them will use a pair of buffers. Treat one of them as the input U concentration and input V concentration, and the other pair as the output U and V concentration. Let's call the first ones U1 and V1, and the second ones, which serve as output, U2 and V2. What I will do in my second descriptor set is that I will flip the roles. So now U2 and V2 become the inputs to the simulation, and U1 and V1 becomes the outputs. With this, I can bring back the double buffering pattern that I already had on the CPU, but this time it's on GPU. There is just one problem with this, is that it breaks a lot of logic that I wrote back in my CPU simulation, because basically back in the day, I assumed that I had a full vision of my data structure and that I could handle inputs and outputs separately, and descriptor sets in Vulkan break this. What I will do then is to introduce a new abstraction that I call the UV set, which represents one Vulkan descriptor set. So pair of inputs, pair of outputs. And it contains 2 things: a Vulkan descriptor set that I can later use when executing my compute pipelines, and the raw underlying buffer that are used as inputs, which I will need by the time I download my GPU data towards the CPU. Actually, this information is already present in this one. The problem is that descriptor sets are very generic abstraction. They can contain a lot more than buffers about many obscure GPU memory resource types that you've not heard of. And this means that fetching a particular set of buffers from a descriptor set is a bit of a pain. So considering that Vulkan uses reference counting everywhere, you know, I can just have another copy of my buffer reference counted pointer. It's not going to ruin my memory, and it works. The setup is going to be tricky as well, because remember, I have 4 buffers, and they play different roles in the 2 descriptor sets that I'm going to build. Which means that now I cannot build buffers in the constructor of my descriptor sets, because they will need to be the 4 same buffers, right? Which is why I need to do something a little dirty here by having 2 different constructors, one that builds 4 buffers, one that takes 4 buffers and put them together into a descriptor set, and then I leave the rest as a concern to the caller, which is going to be my concentration struct that does the double buffering. Not the best software engineering in the world, gets the job done. The buffer allocation looks like this. I can get from my command line option how big my simulation domain is. Because now I have 0 padding, I need to remember to add the padding to this for the rows, for the columns. Then I can use a new slice constructor from the Vulkan buffer abstraction. By default, it builds GPU buffers because that's what you use most of the time. So I have less parameters to tune. But what I do need to tune is to tell Vulkan early on the ways in which I'm going to use these buffers. There are 2 usages here that should be obvious to you and one which should be more surprising to you. I need the storage buffer usage because eventually I'm going to take these buffers and bind them to my compute pipeline as a storage buffer. Okay. And I also need the transfer source usage because at some point I'm going to take my GPU data and download it to the CPU. So far, so good. But if you have been following what I've been saying earlier, you may be wondering where this one is coming from. Because I have a GPU side initialization, so I should not need to transfer data from the CPU to the GPU. We will get back to this, but essentially the reason why I need that is that one of the buffers that I'm building, I'm going to set it to a bunch of zeros using an optimized Vulkan routine called the clear command, which is basically a memset for GPUs. And for some reason, the Vulkan API designers, in their great wisdom, decide that this was kind of a memory transfer destination. Then, you know, I need to have this number of elements, which is the product of my rows and columns, the usual stuff. At this point, I have my 4 buffers. Now, magic is going to happen into the caller. We'll get back to this. And at some point, the caller is going to build the descriptor sets. And what we are going to do is we are going to start from the pipeline layout, which gives us the layout of our descriptor sets. And we are going to say now in this descriptor set, we'll write to the first binding, which is the binding of input buffers. And we are going to write an array of buffers into this binding starting at position 0, which is the first position. And here we are going to put our input buffers for U and V in this order. Then we are going to do the same thing for the second binding, which I call the output binding. Again, starting at position 0, but this time for the output buffers. And remember again that what constitutes an input and output buffer is decided by the caller of this function, which means I will later be able to call this flipping the roles of the buffer. Once I have decided how I want to write into my descriptors, I can build the descriptor sets, and the building part is done. Now I mentioned that because I'm doing something a little nasty here, I need to offload some of the concerns to my caller. So let's go look at the caller. Remember that in the CPU simulation, I managed to decouple the concerns so that the concentration struct only took care of double buffering a pair of concentration and alternatively treating one as input, one as output. Here, unfortunately, it will have to do a bit more work. The beginning of the adaptation is easy. Before we had UV pairs, now we have pairs of descriptor sets, which, thanks to reference counting, is not as expensive as it may sound. But now we have this small function called create and schedule init. What it's going to do is it's going to create the 4 buffers, the associated descriptor set, and it's going to enqueue in a Vulkan command buffer the commands necessary to initialize the data inside of our various buffers. So we start by allocating our buffers, 4 of them. Here I need to play a dirty trick because arrays are hard, essentially. We can go more into detail of this if you want. And then I build my descriptor sets, flipping the roles of U1, U2, V1, V2, as I mentioned. So far, so good. Now I want to prepare to initialize my data. For the data that's going to serve as the first input of my simulation, I'm going to use the initialization compute pipeline that I mentioned earlier. So I'm going to perform GPU-side initialization so that I do not need to do a copy from the CPU to the GPU. So I bind the pipeline. I bind the resources that it's going to use, which is going to be the second descriptor set, because the output of the second descriptor set is the input to the first descriptor set, which is the first one we're going to use later on. I need to compute my work group, my number of work groups correctly. And again, I'm thankful to use a programming language that has diffcil. Every programming language should have this. So it's the padded number of elements divided by the user requested workgroup size, rounding up, because we need to handle the trailing elements, even if they do not fill an entire GPU workgroup. Once that is done, I am ready to execute my initialization pipeline. And this is unsafe because Vulkan cannot check for us that our GPU code is not going to have any undefined behavior. It tried to help us at the previous steps, but the GPU kernel parts, we are no, sorry. Maybe something for future GPU APIs built on top of Vulkan. What about the second set of buffers? You may think that we do not need to initialize them at all, but that would be forgetting about the zero boundaries. We still have those to take care of. We could have a dedicated GPU kernel which only sets the boundary to 0. But your GPU driver has a very fast memset-ish implementation. It does not cost a lot to generate zeros that we don't care about. Especially since we are only going to do the initialization on the first simulation run. And in a real-world simulation, we should be doing many simulation steps. So all this will be amortized. Also, it saves us from the work of writing one more GPU compute pipeline. So I will take the lazy route here and just treat my buffers, which contains floating point data, into a buffer that contains integer data, because for some reason, Vulkan only supports filling buffers with integers. But 0 in integer is the same as 0 in float. Life is nice. And in the end, I am ready. Well, at least I will be ready after this command buffer has been executed. The rest will be similar. We drop the shape accessor because, as you will see later on, we are not going to need it anymore. The current accessor is easy to adapt. The update part actually becomes simpler because before we used to decide which buffer is the input, which is the output. No, we don't. We are using descriptor set, which contain both inputs and outputs, and we just take the current descriptor set and flip the descriptor set each time. We do have, however, a new GPU-specific concern to take care of, which wasn't there before, which is that in the world of GPU, every single operation is fallible. And this includes whatever we are going to do with this descriptor set. So we need to handle the possibility of this user function returning an error, and if there is an error, propagate it to the caller. Finally, we do not need to send input from the CPU to the GPU, but we do still need to get the outputs back from the CPU. Here we could have adapted the UV struct that we used to have before, which contains a pair of concentration for U and V synchronized. But we actually need to think about what we want here. Our main goal is to write down the concentration of the V species to HDF5 and the V species only. We are not using the concentration of the U species. If we start building now abstractions around the pair of species, it means that to be consistent with ourselves, we are going to need to download twice the volume of data, of which we will only be using half. So as long as we are very confident that we only need the V species concentration, it's better to switch to an abstraction which is specific to the V species only. Well, I could make it more generic by saying it's any species, but since I only care about the V species right now, I do the simplest code that will possibly work. And here I need the buffer as usual. And much like on the GPU side, I do have a problem, which is that I have a buffer, but I don't know how its elements map into rows and columns. So I will play the same trick as I did before, which is to keep around the length of my lines so that later I can do 2D computations without asking users to pass me the parameters of the simulation over and over again so that I can discover it again. So how is it set up? This looks very much like the buffers we have set up previously. If this were production code, I would consider duplicating the code. I need to, as usual, compute the full size of my buffer, including paddings. I mentioned, padding compared to variable size stencils, you win in one area, you lose in another. Pick your poison. I need this buffer to be suitable for downloading data from the GPU to the CPU. That part is hopefully obvious. And I ask the memory to be, if possible, allocated on the CPU side, because I'm going later to access it from the CPU side or to do the HDF5 writing. And to be suitable for random access, because I don't know what HDF5 is going to do, but it will must certainly not be a sequential write. The rest is as before, so I don't think it's worth commenting. I then add a method which allows me, starting from this buffer, to schedule an update to it. This is part of a strategy which I mentioned in the previous part of the course, where before I used to have this huge function that did everything with command buffers, and it ended up being a quite complex function with many parameters, and I would like to break it down into smaller GPU transactions in the interest of keeping code intelligible. So here, it's just a buffer copy. We start from the V part of our set of resources, which, remember, is the input part. And we download it to our internal CPU buffer. Finally, we want to allow users to access this data as a two-dimensional array. One-dimensional array are something we have to do internally because Vulkan does not know any better. But we don't want to expose this to our user. We want them to think that the world is 2D and memory is 2D and everything's nice. So we have this function, which has a bit of a weird interface design. You would expect maybe this function to return an array, a two-dimensional array, which actually it cannot do, or at least not without going through some very dirty tricks. Because Vulkan is trying to protect us from data races between the CPU side and the GPU side. And the way it does that is that it gives us RAII objects that allow us to acquire a kind of read lock from our buffers. The idea here is when I want to read a buffer, I ask Vulkan to read from it. It checks that I did not mess up by trying to read to something that the GPU is currently writing to. If it's all good, it gives me an accessor, and as long as this accessor is active, Vulkan will not schedule any command that writes to this buffer on the GPU side. And this way, memory safety is achieved. Once I have this temporary, it has a destructor. In Rust, we use the drop trait for that, which will ensure that once I'm done accessing this data and it's not reachable anymore, the lock will be released, and I can use this with a GPU code again. I will then proceed to do the same computation that I have done too many times already. Again, some candidate for later code refactoring to have this in less different places until I know how many rows and columns I have. And then I can use ND-array to turn my one-dimensional data set into a two-dimensional view. Once I have this view, remember that view still includes our 0 elements on the sides. That's an implementation detail, right? We don't want to expose that to the user. The user shouldn't care whether we chose to have irregular stencils or 0 padding values. So what we will do is we will slice this two-dimensional array to only take the center part and only expose that to our user. So the user doesn't need to care that we have 0 padding. And once we have done all this, we can finally call the user callback, which will accept this two-dimensional array view, do whatever the user wants with it, and at the end, return some result that we are going to forward to the caller. There is one last step, which I wish didn't exist, but currently it does. The AZA5 binding that I am using will not allow me to write to AZA5 data which is not contiguous in memory, which is not the case here because remember, we have hidden the 0 padding elements. So I'm not fully up to date on my AZA5, but I'm pretty sure that's a Rust binding limitation, not an AZA5 C library limitation, so it should probably be fixed. But in any case, we can work around it in a dirty way, like all workarounds, by just making a contiguous copy of our data for now. If this becomes a performance problem, we'll fix it later on in the optimization section. The rest is as before. Are there any questions on this part? If not, I propose that we conclude for now, have a coffee break. We will get back at 4 p.m. for more the last word on this story. And have a nice break.